Sequence. Essential questions. What is a sequence? What is an arithmetic and geometric sequence? How do you graph a sequence? What does the limit of a sequence reveal? In our experience, a sequence is a list of numbers. Every one of the numbers in the list is called a term. It can be finite or infinite. Take a minute to finish the sequences listed above. Arithmetic sequence can be written in a form where every term is based on a constant difference. So each term in the sequence can be obtained recursively from the previous term or with an explicit formula. Let's take a look at your answers and how we should have finished the description of an arithmetic sequence. Again, let's take a look at the two types of formulas we can use for an arithmetic sequence. A recursive one, it builds from the previous term. So we take the previous term and we add the common difference to it each time. In the explicit formula, we have to start with the first term and then add the multiple differences until we get to the term that we want. So to find the 10th term, we would use the explicit formula to get there a lot faster and get to -47. Next type of sequence is geometric, and this is where each term's, the ratio between the next term and the previous term have a common ratio. Go ahead and try to fill out the sequence for geometric sequence and its definition. Okay, here are the answers. So the common ratio is based on the next term divided by the previous term, and this is called the ratio of the sequence. In recursive form, you would base it upon the previous term times that ratio. For the explicit form, you would have to take the first term and multiply by the ratio to some exponent determined by the term number that you want to get to. Graphing a sequence. Let's take a look at how to do that. One way is you could use parametric mode, which I have already here. And then I go ahead into y equals. Now the x sub 1 is really just indicating the term number, and it's the y sub 1 that's determining the value of the term. Using the window they suggest, I'm going to go ahead and graph it, and this is what the graph looks like. And you can see that it oscillates from -1 to +1 because the term has a factor -1 to the n, and when n is even, the term is positive, and when it's odd, it'll be negative. We can also use the sequence mode in our calculator, so let's go to mode, and I'm going to go down to sequence and show you how we can graph the sequence in sequence mode. Now the suggestion is that our formula is a recursive formula, u sub n-1, using the previous term, and we're going to add 2, and our first term is 4. I'm going to change the window to the suggestion that they have there, and it wants us to go to x is 0 to 10, and then our y is going to be, our suggestion is -5 to 25, factor of 5. And let's go ahead and graph. And you can see that it is a sequence, a series of numbers that when they graph without bound. They seem to increase. Let's talk about the word monotonic. Monotonic sequence is a sequence whose terms get successfully larger or smaller. And so here are 4 examples. The first one, monotonic and bounded. In other words, it's getting bigger and bigger, but it won't get past a certain number. And the next one is non-monotonic, which oscillating back and forth between 2 different values. Next one is non-monotonic because it increases and then decreases. Last one is monotonic and bounded. This time it has a lower bound instead of an upper bound like the first one. Okay, so let's go ahead and take a look at a definition of when a sequence converges. So the limit L as n approaches infinity, if given any positive number epsilon, there is a positive number m, such that for all n greater than m, we have this difference between the term and the limit will be within an epsilon, or a very small number. Now what does that look like? Well, in this graph right here, you can see this graph right here, the a sub n terms are getting closer and closer to one particular value. They oscillate back and forth, but notice that as we get past m and we go to the a sub n, as it goes farther and farther, goes to infinity, that the difference between this a sub n term and the limit, the difference between these two values right here, is going to be very small. It's going to be within an epsilon neighborhood of it. So that's what approaching a limit for a sequence looks like. Now the properties of a limit for limits with sequences is such that if you have the limit of two sequences being added, then you're just adding the limit of each sequence added together, and the difference rule, product rule, constant multiple rule, and quotient rule. Let's take a look at finding the limit of this sequence. First, let's do it graphically. And so we're going to go ahead and go to y equals. I am going to go ahead and clear this and write that, which is parentheses 2. Just hit your variable key, minus 1, and then divided by, and then the variable. And our first term is going to be, when I'm going to let it be start at 1, and so when I let it be 1, that's going to be 1 as well. I want my window, I'll change my window, 0 to 20. And then I'm going to go down here, 0 to 20. And now I'm going to go from -1 to 3 by 1. And we'll go ahead and graph. All right, now notice that this looks monotonic and it looks like it's bounded. It looks like it's getting closer and closer to one particular value, and the difference between the a sub n term and the limit will be within an epsilon neighborhood. Now, so it does look like it converges, and now we can do it analytically. So we're going to take the limit of this expression, and when we do that, we take the limit of the difference, and we find that the answer is 2, and that graphically that looks like is what is happening here. Okay, now let's take a look at determining the convergence or divergence of this sequence right here. So I'm going to take the limit as n approaches infinity of -1 to the n all over 2n plus 1 over n, which is the same thing as taking the limit of each part of the product. So that's going to be this. Now, in the previous example, we did find that this limit was 2. But this limit doesn't have a limit. This does not exist. And that's because if n is even, this will be +1, and if it's odd, it's -1. So when this doesn't exist, then the whole thing doesn't exist. Now let's go ahead and take a look at what the picture looks like on our calculator. So we're going to go to y equal, and I'm going to insert, second insert, and I'm going to write parentheses -1 to the nth power. And when I let n equal to 1, I am going to get -1 as my answer here. And let's see, I'm going to get not -1, I'm going to, when I let it be 1, it'll be -1, and then 1 will be, so that'll be -3. Okay, and let me go ahead and change my window. I need to see a little bit more. So I'll go from -5 to 5. Now let's go ahead and graph. And you can see that it's oscillating back and forth between -1 and 1, and it's not going to meet the definition, the epsilon definition that's required. All right, let's take a look at the sandwich theorem for sequences. If you have two sequences that you know their limit and an unknown sequence is between them, and these two sequences approach the same number, then the one that's sandwiched between must also have the same number. Take a look at this example right here where we're looking for the sequence by cosine n over n, and we find its limit by examining 1 over n on the right hand side and -1 over n on the left hand side, finding those limits and knowing that the limit of the sequence in between has to be the same. Now, I can't tell you enough how important this thing is going to be, so make sure you really put a triple star here. The absolute value theorem. The sandwich theorem is this absolute value theorem, which is so important to what we're going to do in the next 9 weeks. The limit as n approaches infinity of the a sub n term, the absolute value of the a sub n term is equal to 0. If this occurs, then the limit as n approaches infinity of a sub n, where a sub n could be positive or negative, will also equal 0. Now let's take a look at why that is. A sub n, which could be positive and negative, is between its positive value and its negative value. And as n approaches infinity, we have been told that its absolute value is going to 0. So we know that this part right here, we know that its limit will eventually go to 0. And we know that the opposite of this will also be 0. So these two, the limits will be equal to 0. So that means this one in between must also equal to 0. This is the absolute value theorem. All right, let's take a look at solving this problem, number 6. Number 6, we want to find the limit as n approaches infinity of -1 to the nth term 3n minus 1 over n squared. Now to do that, I'm going to find the limit as n approaches infinity of the absolute value of -1 to the n times 3n minus 1 over n squared. I'm going to use a theorem that we just talked about. So this really amounts to just looking at this term right here, 3n minus 1 over n squared, because whether it's positive or negative really depends on this factor right here, and I'm just looking at its absolute value. And I can see that when I separate these, this is going to be 3 over n minus 1 over n squared, that both of these are going to go to 0, and so this value is 0. So I know that the limit as n approaches infinity of the absolute value of -1 to the n times 3n minus 1 over n squared is equal to 0. So by that theorem, I know that the limit as n approaches infinity of -1 to the n, 3n minus 1 over n squared will also be equal to 0. And you can actually graph it on your calculator to see that that's what's happening. Now, how is that different from the number 5 that we just finished doing? And the difference is that this limit did not go to 0. This limit went to 2. And so we could not invoke that theorem. Okay, last one, number 7. Use the sandwich theorem to show that this sequence converges and find its limit. Remember that n factorial looks like this: 0 factorial, 1 factorial, and so on. And we know that the limit of 1 over n as n approaches infinity is equal to 0. So this 1 over n factorial is caught between these two sequences here. Now let's check just to make sure that you understand that. When n is equal to 1, notice that this is true. When n is equal to 2, notice this is true, 3, this is true, 4, this is true. So I hope I've convinced you that 1 over n factorial is between these two values. And when I take the limit of all three expressions, we find the left and right are 0, so the one in the middle is 0.